So earlier in this course, we started to discuss how we use distributed circuits, rather than lumped circuits, at radio frequencies. We're not doing a circuit design course here, but it is useful to explain a little bit more about the relationship between high frequencies, and how nearly impossible it is to draw a circuit diagram that accurately represents the behavior of an RF circuit. So as an example, let's consider a coil of wire, which is what this diagram on the lower left shows. If we have a certain number of turns of wire of a certain radius, then it's possible to calculate what the inductance is of that coil of wire. As we pass current through it, it sets up a magnetic field, and the magnetic field takes a while to grow, and then when we take the current away, it takes a while for it to decay away again. And the amount of energy stored in that magnetic field is a property that we think of in terms of its inductance. So this inductance, or L term here, means that the more turns it has, or the bigger its radius, the more magnetic energy it can hold. And the omega here is a Greek symbol, representing frequency. At higher frequencies, it's more difficult to actually get current to change direction in an inductor, because the inductance resists changes in current, and the faster we try to change it, the more it resists. So it's difficult to explain in just a few words what we mean by an inductor, but this coil of wire is a basic circuit building block. And even if we don't coil up a piece of wire, it still has a small amount of inductance associated with it. There is a concept called Z, which stands for impedance. This has a combination of resistive losses and inductance. Resistive losses are related to how much current flows through a wire, which dissipates power in the form of heat. And then there's the inductive component, which is to do with energy storage. It doesn't actually use up energy, it just holds it for a little while in the magnetic field, before returning it a short time later. Those two components completely define that term Z, at a particular operating frequency. So we can predict how the inductor will behave electrically. And that's how we normally analyze a circuit which contains an inductor. We just need to know those two parts, its resistive part and its inductive part, and its behavior can be figured out. At higher frequencies, this approach doesn't work. It goes wrong in the sense that it takes some time for a signal to go through an inductor. And so we have to take into account the delay time between the signal going in the front, and coming out the back of the inductor. We have to split up the inductor into smaller and smaller chunks, in order to accurately produce a model that represents its electrical behavior. We take the overall resistance here, and cut it into lots of smaller series parts of resistance, each one of which has its own elemental bit of inductance. And then, between each adjacent turn of the inductor, there's a little bit of parasitic capacitance, which now becomes significant, because at higher frequencies, capacitors conduct signals, and become more and more of a problem. And so in order to model this inductor in terms of regular circuit components, we have to use many resistors, capacitors, and inductors, to make an equivalent circuit of it. And as we go higher in frequency, this becomes a more elaborate task. So it's a no-brainer really, and we can't really use elemental lumped circuit analysis at radio frequencies, since it just gets too complicated. There is a different way, and in the meantime, we just have to acknowledge that it takes time for signals to go through elements, and we therefore have to model them in a different way.